Let's look at what happens when you combine a p-type semiconductor with an n-type semiconductor. This forms what we call a p-n junction, and it has a peculiar property that allows conduction of electricity in one direction from p to n rather than in the opposite direction. This allows a p-n junction to be used as a diode. When you put p and n-type material together, there will be a formation of a depletion area. The electrons in the n-type will be attracted by the holes in the p-type which are positive, and the holes which are positive in the p-type will be attracted by the electrons that are negative in the n-type material. These holes and electrons will combine together in the middle and hence create a zone where there's no charge carriers, which doesn't allow electricity to flow through in a certain direction. So once again, you see here that the electrons flow through, leaves the n-type and combines with the holes on the left hand side, and the holes on the left hand side combines with the electrons on the right hand side. They form a zone of no charge carriers, depletion region. This depletion region is the depletion of charge carriers. However, once the electron leaves the n-type, it leaves behind positive charges, and once the hole leaves the p-type semiconductor, it leaves behind negative charges. This forms an electric field pointing from the n-type semiconductor towards the p-type semiconductor. The electrons diffusing away from the n-type semiconductor leaves behind a region which is positively charged, and the holes diffusing away from the p-type semiconductor leaves behind a region which is negatively charged. This causes an electrical potential to be set up and an electric field pointing from n-types towards the p-type. This makes it harder for more electrons to diffuse over the p-n junction because it is already negative on the p semiconductor side. This makes it also difficult for the holes to move over to the n-type because that side is already positively charged. Thus, only electrons and holes which possess sufficient kinetic energy will be able to overcome this electrical force and climb the potential hill to the other side. Equilibrium is reached when the above potential difference in the depletion region increases to a value that causes a net movement of electrons and holes across the p-n junction to be 0. You see here, this is the electrical potential. It is higher on the n side and lower on the p side, and the electrical potential energy of an electron, very carefully, is an electron will be higher on the left hand side and lower on the right hand side. Now if you contact a battery in the reverse bias, no electricity will be conducted. So if we look at the symbol of a diode, we know that the n-type is actually represented, can be imagined to be represented by the straight line, and the p-type to be represented by the triangle. And we see very clearly here that the current will not be able to flow through because it's pointing in the wrong direction of the diode. How does this actually happen? The positive side of the battery will draw the electrons further away from the center, causing an even larger area of zone of depletion, whereas on the negative side of the battery, you will draw away the holes on the left hand side, also increasing the zone of depletion. Hence, when you connect a battery in the reverse bias to a diode, the zone of depletion is enlarged. This causes the electrical potential across to be larger and the potential energy drop to be larger from the left to the right, or rather an increase in potential energy from the right to the left is made larger, making it harder for electrons to flow through. If you however connect it in the positive bias, the positive charge or positive potential of the battery will force the holes in the p-type material to move closer to the center, and the negative charge of the battery will force the electrons to move closer to the center. What this essentially does is it narrows the zone of depletion. This also reduces the potential difference and the potential energy difference across the n and p type. Hence, it reduces it to an extent that an appreciable current flows in the direction from p-type semiconductor to n-type semiconductor. This means that if you connect a battery semiconductor in a forward bias to a battery, as the V increase, the I increases by much more, which means that the resistance of the PN junction works much like a intrinsic semiconductor. However, when connected in the negative bias, you can see that the current for an increase, you require a large increase in V, and you have almost no increase in I. And once it is close to a certain breakdown voltage, you can see that the diode is spoiled and the voltage, the current increases by a lot for almost no change in V. And now I've introduced to you the fifth type of IV characteristic graph over the ohmic conductor, the filament lamp, the thermistor, and the intrinsic semiconductor.